Have you ever stopped to think about how all the invisible signals that run our world, for your Wi-Fi, your phone, your Bluetooth, are designed to work so flawlessly? Well, today, we're diving into an incredibly powerful piece of software called HFSS. This is the virtual drawing board that engineers use to build our wireless reality before a single piece of hardware is ever made. So here's how we're going to break it all down. First, we'll tackle the big problem that HFSS was created to solve. Then we'll take a peek inside the software's digital toolbox. After that, we'll walk through the actual design process and even build a simple antenna together, step by step. And finally, we'll zoom out and see why all of this is so important in our super connected world. All right, let's get right to it. Before we can appreciate the solution, we really need to understand the fundamental challenge engineers are up against when they're working with wireless tech. Really think about that for a second. You can't see a Wi-Fi signal. You can't touch it. You can't hold a 5G radio wave in your hand. So how on earth do you engineer a tiny, incredibly complex antenna system for a new smartphone and be absolutely sure it's going to work before spending millions of dollars to actually build it? And this right here is the answer. It's HFSS, which stands for High Frequency Structure Simulator. The best way to think about it is as a virtual physics lab on a computer. It uses the fundamental laws of electromagnetism, we're talking Maxwell's equations here, to let engineers build, test, and perfect their designs in a digital world with stunning accuracy. And the crazy thing is just how many places this software shows up. It is everywhere. From the phone that's probably in your pocket right now, to the satellites beaming down GPS signals from space, even in advanced radar systems and all those little smart devices that make up the Internet of Things. HFSS is the hidden engine behind so much of it. Okay, so now let's go inside the program. We're going to look at the basic building blocks an engineer gets to play with. Think of it like they're digital clay. Everything you build in HFSS starts with some really simple shapes. On one hand, you have 2D sheets. These are totally flat objects, like a piece of paper. You'd use these for things like the thin layers of copper on a circuit board. And then you have 3D solids, things like boxes, cylinders, spheres that have real volume. These represent the physical, chunky parts, like the insulating board itself. Now here's where it gets really cool. You don't just draw complicated things from scratch. You create them using what are called Boolean operations. You can take two shapes and unite them, fusing them into one. Or you can use one shape as a kind of cookie cutter, a tool to subtract a piece from another shape. It's basically digital sculpting, and it lets you create almost any geometry you can imagine. But, of course, a shape is just a shape. To make the simulation work, you have to tell the software what everything is made of. You dip into this huge library of materials and assign them. Is this piece of metal copper or aluminum? Is that insulating block made of FR4, a common circuit board material, or maybe Teflon? This step is absolutely crucial for making sure the virtual model acts just like the real thing would. So now that we've got the building blocks down, let's talk about the process. There's a really standard workflow that engineers follow to get from a back-of-the-napkin idea to a fully analyzed result. It's a really logical step-by-step cycle. You start with your concept and you build the 3D model. Then you assign all the materials, just like we talked about. Next, you have to set up the rules of the simulation. You define the space around your device and you tell the software where the signal gets injected. Then comes the magic part. The software breaks your model down into thousands, sometimes millions of tiny tetrahedrons, a process called meshing, and solves the complex physics for each one. And finally, you get to analyze the results, see how it performs, and then, this is the most important part, you go back and tweak the design to make it even better. Okay, theory is great and all, but I think it's way more fun to see this stuff in action. So let's actually build something. We're going to put together a simple microstrip patch antenna, which is one of the most common types of antennas out there. Right, so this is a real workhorse design. You'd find something just like it inside a Wi-Fi router or other wireless devices. The best way to picture it is like a little 3-layer sandwich. First up, we lay down the foundation. We start by drawing a simple, flat 2D rectangle. This is going to be our ground plane, which acts as a common electrical reference point for the whole antenna. It's the bottom piece of bread in our sandwich. Next, right on top of that ground plane, we draw a 3D box. This is our substrate, the filling of the sandwich. It's an insulator. And just like we talked about, we go into the material library and tell the software this box is made of FR4, that standard circuit board material. And for our final layer, the top piece of bread, we draw two more flat 2D rectangles. The bigger one is called the patch, and that's the part that actually radiates the radio waves out into the world. The smaller, thinner one is the feed line, and its job is to carry the signal to the patch. Okay, the model is built, but now we have to get it ready to simulate. We use that unite command to make the patch and feed one single object. Then we assign boundaries, telling HFSS that the metallic parts are perfect conductors. Then we add an excitation, which is basically like hooking up a virtual cable to the feed line to inject our test signal. And last, we draw a big box around the whole antenna to tell the software, hey, calculate how the signal radiates out into the space. Now, it's super important to remember that antennas are designed for very specific frequencies. The dimensions of our patch antenna were carefully chosen to work at 2.4 gigahertz. And that's no accident. That's the frequency band used by tons of devices, like Wi-Fi and Bluetooth. So we're specifically testing to see if it performs well right there. So, did it work? This is the moment of truth. The simulation spits out this graph, and what we're looking for is that deep dip right in the middle of the plot. And there it is. That sharp V shape tells us that our antenna is resonating perfectly. It's efficiently taking the signal we fed it and launching it as a radio wave right around our target of 2.4 gigahertz. It works. That's a successful design. All right, so we've seen the process. We've built a virtual antenna, and we've confirmed that it works. Now, let's just zoom out for a minute and talk about the bigger picture here. Why a tool like this is such a game changer. The real power of HFSS really boils down to a few key things. First, it's incredibly accurate. The simulation results match up amazingly well with real-world tests. It's also super versatile. You can design just about anything with it. But maybe the coolest part is the visualization. It lets engineers literally see the invisible electromagnetic fields, giving them an intuition they could never get otherwise. And finally, its optimization tools can automatically tweak designs for you, saving an unbelievable amount of time and money on failed prototypes. And this really sums it all up, doesn't it? This kind of software isn't just a nice-to-have. It's a completely essential, indispensable part of the modern engineer's toolkit. It is fundamentally what allows them to keep pushing the boundaries and inventing the future of how we all stay connected. And that kind of leaves us with one final thing to think about. We all want our devices to get smaller, faster, and more powerful every single year. So to keep up with those demands, the virtual design tools engineers rely on will have to evolve too. They'll need to get even faster, even smarter, and even more predictive. The race to design the future of technology is really happening right here, inside the simulation.